Thanks, thanks Noga, and thanks for inviting me here. I'm really so happy to be here in this celebration for Endre and the receiving of the Abel Prize. I think some people mentioned here that how Endre was one of the earliest, among the earliest mathematicians to recognize the importance of theoretical computer science. I can tell you for a fact that theoretical computer science recognized the importance of Endre Szemerédi very early on. And you'll see some examples of this. I was instructed to give the science lecture, which is supposed to be about some aspect of mathematics on which Endre had influence, but rather than talk about his work, as my two predecessors did, I'm supposed to talk about just this research area, and I'll of course point out some contributions of Endre, but what I really want to tell you about for this hour is about randomness, and randomness, the way it is viewed through, if you want, the lens of computation. Now, randomness is something that essentially everybody has some feeling about. I mean, from a very young age, we are talking about luck and chance and lotteries, and people come, both laymen and scientists come with their own notions and understanding of randomness, and indeed also within mathematics, this very notion received many, has many approaches towards understanding it. There are various definitions, and all of them important. And what I want to tell you about today is that when you view things computationally, you get yet another viewpoint of it, and this viewpoint connects very well to some mathematical disciplines and some aspects of randomness that were mentioned here, and in particular this notion of pseudorandomness that I'll try to explain. So here's a plan for the talk. Before I even start, I want to make sure that I'm talking only about discrete probability. In fact, I'm going to talk about the simplest kind of randomness that you can imagine. My basic random object will be a coin toss that's 50% tails and 50% heads. And we'll just have sequences of this. So here I have two sequences of coin tosses, each produced with independent tosses of a coin. Which one is more probable, the top one or the bottom? Good, so everybody, I really want to make sure that that's the randomness you have to understand. Each of them are equally probable. There's 20 coin tosses, the probability of each is 1/2 to the 20. That's perfect randomness, that's a uniform distribution. Okay, now what is it good for? What do we do with coin tosses? Well, actually, we'll see that, many examples where it's useful. We see lots of examples where it's useful. And then, we'll wonder, are all these wonderful applications of randomness real? I mean, do we really have access to such perfect randomness? And we'll keep this question in the back of our mind and talk about pseudorandomness. And pseudorandomness, as you see, is a very general, broad definition, vague somewhat. It's just deterministic structures. So pseudorandom structures are deterministic, well-defined structures, which share some properties of random ones. Some properties of random. And we'll see lots of examples and sort of applications and connections to mathematics there. And at the end, we'll go back to our question and try to understand which of the applications of perfect randomness actually survive in a world in which there is no randomness at all, or maybe there is weak forms of randomness. And we'll see how this pseudorandomness view, which will be computational, will help us understanding some answers to this question. Okay, so let me start with the power of randomness. So And I really encourage you, and I'll remind you on every slide, to think about, where actually do we get these coin tosses in all these applications. Okay, perhaps the most amazing, I would say, and powerful and simple application of randomness that you see every day is in sampling. So you want to know who will win the next election in the US. There are 280 million people. Maybe not all of them are registered voters, but anyway, a huge number. You want to know what will happen. Well, you can go and ask everyone what they'll vote, but it's much simpler to just pick a small sample. Let's say you pick 2,000 people at random, using perfect randomness. Then it turns out that the following is true. Such a sample will be perfect with very high probability. It will be, with 99% probability, will tell you, will predict the outcome up to plus minus of 2%. This is a remarkable theorem, the law of large numbers. And in particular, this number, 2,000, suffices to give you these accuracy parameters, no matter if you have 200 million or billion or trillion people. It's really independent of the population size. So that's extremely powerful, of course, in science, in statistics, and politics, that you are able to do that. That you are saving, you are doing a tiny amount of work, and you get a highly accurate estimate. And if you had no randomness, if you were doing it deterministically, and you wanted 2% accuracy here, well, you'll have to ask 98% of the population, 99%. Okay, so it's a huge, very, very powerful use of randomness. I could give an hour or a whole semester course on application. I'll try to give examples of very different applications, and each of them have many, many siblings. So this is sort of typical statistical application. Here's our question. If we don't have this perfect randomness, what do we do? Here's a very different application. So this is to efficient probabilistic algorithms. This particular problem comes from physics or chemistry. You are given a region in space. It doesn't have to be square. It can be any region. And you ask how many ways are there to tile this region with dominoes, 2-by-1 dominoes like here. And it can be huge. This is called the dimer problem in physics, and the reason physicists and chemists study it is to understand. It really reveals properties of nature, very basic properties like free energy in this system, phase transitions, Gibbs distributions, and so on. But it's a basic counting problem, combinatorial counting problem. Now, this number is huge. If you went and tried all the possibilities of fitting the dominoes, it'll take you a long time. It turns out that randomly, so if you have a computer program that's allowed to toss coins, you can finish the task very quickly, efficiently in the size of this region. This particular results of Randall and Sinclair, and it will approximately count the number of tilings using a method that's sometimes called the Monte Carlo method, what von Neumann and Ulam invented for the nuclear project. Again, this will be an efficient thing, polynomial if it's n by n, or roughly if there are n sites in this region, it will finish with polynomial time in n very efficiently. If you try to do it deterministically, just without randomness, the best algorithm we'll have is not much faster than just trying all possibilities. It's terrible. It's exponential time, and we will never do it for any reasonable size shape. I stress that here, that's the best known deterministic algorithm. Maybe there are much faster ones, but we don't know them. And again, probabilistic algorithms which do exponentially better than their deterministic counterparts, we have lots and lots of examples. This is just one. And again, here we would like to, ask ourselves, what do we do if, without this perfect randomness? Here's another very different type of use of randomness. this is to distributed computation, to situation where the distributed computation usually deals with many parties collaborating or competing, and they don't have a common clock. They don't have some, fixed reference point. So in this particular example of a distributed problem, it's called the dining philosopher's problem. It's a problem of resource allocation. In this case, every program or every philosopher needs two resources. Here the resources are forks, but it could be printers or memory or whatever you want to eat their spaghetti. And the rules are that you should program them in such a way, each should be the same program, such a way that eventually, no one will starve when they want to. So even philosophers, even though they go into this deep contemplation, they sometimes need to eat. So if your program for a philosopher when he or she are hungry would be to, well, grab your right fork and then grab your left fork, you can imagine that it could be that they all simultaneously grab the right fork and never get to eat. So how do you program them? Well, actually, it's a theorem of Dijkstra who suggested this model of this problem, that there is no deterministic solution. So here there is nothing you can do deterministic, not even slow. But if you allow perfect randomness, then there is a probabilistic algorithm, probabilistic programs to each of these guys that will allow them to both think and eat. So it's a very different setting in which randomness just really changes the game from impossible to possible. It's used basically for symmetry breaking. Now, these are examples of things where the task is to do something, and randomness helps to achieve something. But I want to stress that randomness is actually useful not just when you want to do something, but actually when you want to define something, when you want to have a good definition of a mathematical object. And let me give you two examples, very important fields in economics and in cryptography. I'm sure you remember this already. So game theory is about rational behavior of people, of parties, of governments, of companies. And here's a simple game, typical game. It's called the chicken game, which you can think of two companies who are in competition, and each has two possible strategies, being aggressive or being cautious. It's called the chicken game because you should think of these two companies, two young drivers who are on a collision course, and the question, who will swerve first to avoid the collision? Who will be the chicken? But of course, you see that given their strategies, let's say aggressive is you stay on course, and cautious you go to the side. You have payoffs. Each of them gets a payoff. If both of them move aside, then they each get $1 or $1 million, and so on. So this describes the payoffs of the players in a two-party game like this. And the question is, well, in any such a strategic competitive situation, what should people do? Or what describes a rational behavior in such a situation? And Nash, in his award-winning discovery, suggested the Nash equilibrium as a model of rational behavior, saying that rational behavior is, for a set of parties, is strategies for each of them, so that if I know all of your strategies, it's better for me to stay with my own strategy rather than deviate. So it's somehow a notion of stability. And that's what he defined. No player has an incentive to change its strategy given the others. Okay, great, that makes sense. But the fact that it makes sense does not make it a theorem, or certainly not give it a Nobel Prize. What is critical is that it's a useful definition, and in fact, he proved that every game has such a stable strategy, a Nash equilibrium. But this equilibrium is in randomized strategies, in mixed strategies. So randomness is essential for the definition. If you work only with pure strategies, then no such equilibrium exists for most games. Here, the rational behavior will be for every one of these players to toss a coin with probability 3/4, be cautious, with probability 1/4, be aggressive. So randomness is essential for the definition, the very definition of this type of rational behavior. Another extremely important setting where randomness is completely indispensable is cryptography. The very notion of a secret doesn't exist without randomness. So, starting with Shannon and information theory, if I want to choose a password for my login, if you, let's say it's 9 digits, if I toss if I pick a random digit for each, then the probability you'll guess it is 1 in a billion. But if I pick this number, if I pick this password just from the names of my friends, then you'll have a better chance of guessing it. So randomness is essential for generating secrets, and that's just the beginning of a huge line of work in cryptography, and there are lots of wonderful things you can do with cryptography, and that's a subject for different talks. But in all of them, randomness is absolutely essential. And if we don't have it, what do we do if we don't have this perfect randomness? Okay, so that's a question I want you to remember, and now we move to the next step. Well, there's another, randomness is enriching our lives and pouring our lives in many other ways. Okay, so where do we get these perfect random bits? When I don't know the answer to a question, I'm sure you do the same. I go to Google, and I ask Google, where do you get random bits? So you type true random bits, and you get a list. In fact, the list was close to 4 billion answers. And the answer actually is obvious. Where do you get random bits? You buy them, right? There are these companies who would sell you random bits, so that's where you get them. So you actually buy, but you say, well, where do the companies get their random bits? So you look, you actually go into the website, and these guys get it from radioactive decay, and these guys use atmospheric noise. That's from their website, right? So these guys, these two last guys use quantum, phenomena. They measure photons, and so on. So, okay, say, I see, they get it from some physical phenomena that somewhat are unpredictable, and do something with them. They don't tell you. So how do we know that these are good? Or if that's what they are using, maybe it's not perfect randomness, can we use it ourselves, and will we get the same guarantee that all these applications provide if the randomness was perfect? So that's it's a really important question, and in order to understand how to approach a solution to this question, I want you to focus on the next slide, because that's really the most important slide of the lecture. We want to somehow define randomness, and unlike all the definitions that existed before, computation, I'd say the major difference is that definitions, no matter how different they are, what mathematical fields were looking at them, they were objective. They simply define some phenomena to be random or to be non-random or to be somewhat random, the phenomena. And what I want to offer instead is a subjective definition. So let's see what I mean. So we'll do an experiment. I'm going to toss a coin, and you, Randy, will... I always have to pick a victim. I have no coin, but it doesn't matter. The coin is there. So here's the experiment. So we'll do actually 3 repetitions of the same experiment. Each time I'm going to toss a coin. So I'm holding the coin in my hand now. I'm going to flip it, and as it's being flipped, you are supposed to guess whether it will, when it lands on the floor 2 seconds later, whether it will be heads or tails. Okay? So here's the question. If we did it, what do you think are the chances you'll correctly predict the value? 50%, okay. Yes. Good. Okay. I think that's what everybody would answer. I mean, yeah. Okay, good. So now let's change the experiment. I'm going to toss the coin again, but before I do that, I give you a laptop. You just won a laptop. So you have the laptop at your disposal, and now I'm tossing the coin. What's the chance that you'll predict correctly the value when it lands on the floor?
The same.
All right. We practiced it at least 5 times before. I don't know, in Norway they are very serious, and I know that the Abel ceremony was rehearsed very well before we all witnessed it. Okay, so let's change the experiment again. Now I'll give you much more. I'm giving you lots of video cameras around the room looking at my fingers, and they are connected to a huge Cray machine, which is connected to your laptop, and this is already equipped with the programs of all the known physics. And now I'm tossing my coin. What's the chance that you can predict the value when it lands on the floor? 5 times is not enough. Okay, I would say 100% or 99%. What I meant is that, you can, these machines will know the velocity and the rotation and the air humidity, and with enough computational power, at least, maybe 99%. So what's the point? The point is nothing in what I did in creating this random event of a coin toss changed. The same thing happened. But its randomness, it's changed drastically depending on the computational power of the observer. So somehow randomness, according to this view, is in the eye of the beholder, or rather in the computational power of the beholder. It changes how random this phenomena is. And that's the point of view we'll take, okay? So I want to stress, this is sort of a subjective definition of randomness. It's operative. It depends on what something is as random as the application which uses it. Okay? That's how it is operative. So now let's see some demonstrations of it. So I'm going to talk about pseudorandomness, randomness which is somehow good enough in some settings. It's a study of deterministic structures. It can be anything, numbers, graphs, sequences, tables, walks, with some random-like behavior, which we'll need to specify. And different properties will correspond to different applications or different motivations. Mathematics and computer science study pseudorandomness from different angles. Mathematics usually, the objects, the structures are natural things that arise from mathematical, considerations, and they often study random-like properties. In computer science, usually you want what you want some random-like property, and it doesn't have to be in a particular group or ring or graph. You are allowed to just come and construct them as long as you can construct them efficiently. But this is really match made in heaven, and there's so many works, some of which you heard about in the context of Endre Szemerédi's work, and pseudorandomness and order and chaos and so on, but there are many others that, anyway, I will not get into beyond the examples I show you. It's fantastic meeting grounds for mathematicians and computer scientists. So, okay, let's see some examples. And to just, maybe the simplest pseudorandom property I can think of is that of normal numbers. It's both simple, and I'm sure also many people heard about it. So I think you all recognize this number. I want to say what a normal number is. So it's just think of such an infinite decimal expansion. And we call it normal. if the following properties hold. So I'll give you a list of properties, many properties, in fact, infinitely many properties. So what are the properties? I want that every digit will occur in the sequence the right number of times, 1/10. I want that every pair will occur in the sequence the right number of times, 1/100. I want that every triple will occur in the right frequency, 1,000th of the time, etc., etc. So this is a huge list of properties. A number will be normal if it satisfies all of them, and not only in base 10, but in every base. Okay? Oops. In every base. Then we call it normal. So it's a definition. It's a definition that some sequences satisfy, some don't. Okay? 0.11111111 doesn't. Okay. Okay, so what do we know about them? Borel proved that a random real number is normal. So with high probability, almost every real number is normal. So that's when a typical object satisfies it, we call it a pseudorandom property. Okay, and then we may ask ourselves, whether particular objects like pi satisfy it, or E or square root 2, and so on. Okay, so maybe deterministic structures that we know and love satisfy these pseudorandom properties also. In this case, nobody knows. It's an open question. Nobody knows, whether these are no. It's a great open question. Anyway, that's an example of a pseudorandom property. So pseudorandom. So I would say that. So a number, whether a number is normal, is a pseudorandom property because most numbers are normal. Okay. There are many examples. I just want to both connect Endre's work and the two talks you heard to this context, and tell you about two properties, two pseudorandom properties, and in which actually there is some universal pseudorandomness. So let me remind you. I don't have to work hard. Two talks were about this. If you look at this long sequence of integers, in fact, all integers, then they contain a very arbitrarily long arithmetic progression. That's clear. If I just erase many of them, I just take a third of them, just these red ones, they contain oops, I think I made a mistake, but anyway, it doesn't matter. Any third of them will contain an arbitrarily long arithmetic progression, in fact. So, and it's not really difficult to see that if you take a random 1/3 of the, you just pick every integer with probability 1/3, and look at this subset, it will contain arbitrarily long arithmetic progression. So, and it doesn't have to be 1/3, it can be 1/10, 1 in a million, and so on. So then subsequences, if they are random, they contain long arithmetic progressions. So that's a pseudo-random property, okay? Sequence. And now, here's an amazing theorem that you heard enough times today. Every dense subsequence contains it. So in this particular situation is in some sense trivial or universal. Here's the pseudo-random property holds for every sequence of this set. Epsilon regularity, again, we saw if we talk about graphs, an epsilon regular graph is just a graph in which, let's say that's a graph of density of edges P. If you take any subsets of size epsilon, you look at the density between them, the density will be within epsilon of what it was in the whole structure. That's an epsilon regular graph. Now, certainly not all graphs are epsilon regular, and the amazing regularity lemma tells you that nevertheless, if you just break the graph into a few pieces, then you recover it. So a random bipartite graph will be regular. That's, again, very easy to prove, and that's why it's a pseudo-random property. So most bipartite graphs have this property, so it's a pseudo-random property. And Szemerédi's regularity lemma says that every graph can be broken into a few pieces so that most pairs will be epsilon regular. So again, you have some universality. Every graph is not in itself necessarily regular, but can be broken into a few pieces. Most of them would be regular. And we heard talks about the power of this. So you can see that lots of results, in particular of Endre, can be cast in this language of pseudorandomness. You define a property that holds for most structures, and then you ask which deterministic structures have it. Let me go back to other examples. And I want to impress upon you that this view, a pseudorandomness view, appears not only in maybe what some of you may consider esoteric corners of mathematics, but actually in the very, in the most important problems of mathematics. Now, how do we know what are the most important problems of mathematics? Again, we have to go for the money. So I'm sure you recognize this list. That's 7 problems on the Clay Millennium list. The solution of each would give you $1 million, so maybe they are important because of this. Of course, we know that there are better reasons. For those of you who want to make money this way, Endre offered you just $3,000 for the Erdős conjecture. I mean, here you can make $1 million. If you do want to do it, you should remember that 1 is gone already. But you can solve any of the other 6. So at least 2 of these problems are problems about pseudorandomness, and that you may not have realized. So these 2, the P versus NP problem and the Riemann hypothesis, are problems about pseudorandomness. I'll explain to you why. For the P versus NP, so how do problems become problems about pseudorandomness? They have to ask about, like with the normal numbers, is pi normal? They have to ask whether a specific object has a property that most objects do, okay? And in the P versus NP, I'll just say this. Random functions are hard to compute. So that makes hard to compute a pseudorandom property. And the P versus NP question asks whether specific problems, like the traveling salesman problem, or click, or satisfiability, are hard to compute. So it's just like the situation with the normal numbers. Is pi normal is the same? Is TSP hard to compute? Okay? I will not explain this in more detail. Let me explain in somewhat more detail why the Riemann hypothesis is a question about pseudorandom objects. So it's a question about the pseudorandomness of certain walks. So let me explain this here in more detail. So I want to explain the random or drunkard walk. So what's the drunkard walk? I mean, you should think that here in position 0 there is a pub, and someone goes into the pub, has a few beers, comes out, and then starts walking. Well, maybe with probability half it goes up up the street, and probability half goes down the street randomly at every step. Well, how will his position change in time? Well, here are 10 experiments. And one striking feature about this, for people who never saw it, certainly I like to show it to high school kids and so on, is that if you look at 100 time steps and you look at the distance of this person from the origin, he would be quite close to the origin. I mean, this is within 10 or 15 away, even though he walked for 100 steps. So, of course, many of you are familiar with this. Almost surely, for such a random walk, after n steps, the distance from the origin is about square root n, right? That's very easy to prove. So again, a random walk will remain quite close to the origin. So this happens for almost all walks, so it's a pseudo-random property. You can now classify walks and look at particular walks and ask, do they have this property that they stay close to the origin? So now let's look at a particular walk. This is like analog of pi for normal numbers. This is a Möbius walk. So to define the Möbius walk, let me define first this function p of x. if x is an integer, p of x is the number of prime divisors of x, and then mu of x, Möbius function of x, is 0 if the integer has a square divisor, but otherwise it's just plus or minus 1, depending whether the number of prime divisors is odd or even. Now, if we have this, then we have a deterministic walk. You can just look at all the integers. Every integer tells you a value, either 0 or plus minus 1, right? And you can think of this as instructions for somebody walking, you know. It will walk up, walk down, stay in place, walk down, so on, right? So this prescribes a walk. And now the question is whether this walk, this particular Möbius walk, will stay close to the origin as random ones do. Is it pseudorandom? Now here's an amazing theorem. The following are equivalent. One, that this walk will stay close to the origin, like a random one. And second, the Riemann hypothesis. So one way to prove the Riemann hypothesis is to prove that the Möbius walk stays close to the origin. Okay, so we saw that pseudorandomness is important. Now let's, it captures very many different mathematical problems, and in each one you just have to say what is the pseudorandom property you are interested in. Let's look now at a different property, and it will connect us to the questions about what do we do with weak randomness or no randomness, which of the applications we talked about survive. So that's what we want to do. There are many worlds without, you know, without random, well, you can imagine a gradation. So here's my picture. You can just think, we started the lecture describing applications of a world in which we have perfect randomness, and now we are driving along and we are losing randomness as we go, and our tank of randomness is depleting slowly. So I want to explain which of the applications survive if we have some randomness in our world, like maybe this weak, unpredictable physical phenomena that companies are using to produce randomness. And I'll distinguish two cases, one in which several different physical phenomena that produce randomness are independent, and another one, a weaker one, in which there's only, all the randomness in the world is correlated. And we'll end up with an empty tank and wonder what happens if there's absolutely no randomness in the world. The world is deterministic. Which of the applications in the beginning survive? And actually, we'll see that, non-trivial number. Okay, so we had all these wonderful applications of perfect randomness, this unbiased, independent coin tosses. We can do lots of things, statistics, cryptography, algorithms, game theory, etc. And the nature of the world, let's say, is that there are many sources of imperfect randomness that we saw was used by these companies. Maybe sunspots are somewhat random, stock market fluctuations are. Here random, I don't mean in any particular precise sense, but they seem to be unpredictable. I mean, if they were predictable, well, either we will all make lots of money or, well, none of us will make any money. But, I mean, well, we cannot predict them, but they are certainly not perfectly random. I mean, there are weather predictions that are pretty good, even though we don't really know what the weather tomorrow will be. We know that it's more likely it will be like today than not. So there are correlations, there are biases, and so on. The question is, if you have such sources of randomness, what can you do with them? They produce to you. You can sample them. You can get coins from them. But they will be biased and dependent. Now, can you use this somehow to recover randomness, or at least recover some of these applications? Okay. So first, we'll assume that these sources are independent. So whatever happens in the sun does not affect the stock market. Of course, many of you know that there are theories that they do, but let's imagine they don't. So each of them generates some entropy, and we can use them all. So what do we do in this case? So in order to understand what to do in this case, we deviate and we move to another pseudo-randomness question. So I should say this transformation from weak randomness to strong randomness is called extractor theory, a very important theory within theoretical computer science. Here's another pseudo-random property. Suppose you look at a table of numbers. Just imagine a large table of numbers from some range. I'm not going to be very precise. But if the range is big enough, then let's say it's a random table. So you pick the numbers at random. If you look at a small window, a small rectangle, small Cartesian product, and you look at the numbers inside, you'll see that most of them are different from each other. They'll mostly be, you look at any window, there'll be very few collisions, very few agreements. So that's a very, so this theorem here is a very easy theorem to prove. In a random matrix like this, every window is rich, has many, many different entries, integers which are different. If you want numbers, those who like them, let's say we pick windows that are k by k, you have, well, you can have between 0 and quadratic number in k different entries. Let's say that something is rich if it has more superlinear number, let's say k to the 1.1. Distinct entries. It's very easy to prove that in random matrix, appropriate parameters, all tables are rich. So that's our pseudo-random property, okay? That all windows in the matrix are rich. So some tables are pseudo-random, some are not. The question is, can we construct such tables deterministically? A random table is good. The question is whether we can build one explicitly, one that has every submatrix is rich. If you think about it, you'll see it's non-trivial. And one natural way to go about this is to take some natural structure in mathematics, matrices that arise naturally in mathematics, and see whether they themselves are pseudo-random. So, well, here's a table that we encountered in first grade, the addition table. Is it pseudo-random? You look, you see immediately that it's not. Again, arithmetic progressions are here. If you take an arithmetic progression in the rows and in the columns, then you'll have just a linear number of entries. There'll be many collisions. That's certainly not rich. So this is bad. So, okay, well, that was first grade. Let's move to second grade. We can take the multiplication table. And, well, I mean, this is not but anyway, multiplication tables are also bad, right? Because you can take geometric progressions and they'll have the same flaw. Windows built from geometric progressions will have very few distinct entries, just a linear number. So they are also bad. And you think about it and you are reminded of von Neumann's immortal suggestion. Anyone who considers arithmetical methods for producing random digits is, of course, in a state of sin. How many people believe this? I can tell you that von Neumann didn't believe it, and in fact his methods for generating randomness which he needed were certainly not, were arithmetical. So let's forget about it. And let's nevertheless try to generate them arithmetically. So each of these tables are bad, but there is something remarkable, absolutely remarkable, that was discovered by Endre Szemerédi and Paul Erdős. And in a form that we want was discovered, strengthening of it, that's very important, was discovered a few years ago by Bourgain, Katz, and Tau. And here's what the message is. The message is that, well, maybe as you thought, there's a formal way to say that addition and multiplication are different, are very different. They are orthogonal to each other. And the formulation is that, precise formulation is that while each table may be bad, together they are good. So look at any window you want, but look in both of them. There'll be many distinct entries in at least one. So together they are pseudo-random, even though individually they are not. So this window, whatever you look at, you'll find many distinct entries in at least one. So how is it relevant to our question? But it turns out that for this getting pure randomness for many weak sources of randomness, there's a very simple extension of these results I just mentioned about the pseudo-randomness to a sort of a statistical version that tells you that if you want from these weak coins to produce good coins, what you do is just mix addition and multiplication. You add these samples, multiply by this sample, and iterate it a few times. I'm not going to explain it. You get near perfect random coins, which are good for all these applications. So summarizing, having a few weak sources of randomness, of entropy, can be boosted using just these arithmetical methods in order to get really perfect, unbiased, uncorrelated random bits. Okay, that was a strong assumption that we have several independent sources of randomness. Let me move to the next two steps, the next two slides of the last two slides of my lecture, in which we'll see what we can do if this, first of all, what happens when these sources are correlated. So suppose we just have, the sunspots influence everything, all the quantum phenomena and the stock market. So there's just one weak random source. We can produce entropy from it, but certainly not unbiased coin tosses. So here we are going, the applications that will survive will be simply all algorithms, every possible algorithm, probabilistic algorithm. So it doesn't matter how long it takes. How does a probabilistic algorithm look like? Well, it has some input about which it needs to know something, and then it is using some perfect coins. But now we don't have these perfect coins. What do we do? Well, it turns out that if you just feed your biased coins into a typical probabilistic algorithm, it would be useless. Even if these coins are 0.51 heads and 0.49 tails, very close to unbiased, they would be useless for many, many algorithms. So this is really not going, the naive implementation will fail. However, and this requires a lot of detail which I will not give you, you can do something more sophisticated. You can generate, so you can build a more clever algorithm in which from this weak source of randomness, you'll take many more bits. If you needed n bits here, you'll take maybe n cubed bits, which have some entropy, maybe n squared amount of entropy lying hidden somewhere here. You'll generate from them using this wonderful pseudo-random objects, which we call an extractor, a collection of potential sequences to feed into your algorithm. You'll try all of them. You'll try all of them on your original algorithm and take a majority vote. So rather than trying just one, you'll, from this sample, this sort of perfect sample, you'll create, you'll try them all and apply the original algorithm, take a majority vote. And this turns out to work because there is a way, this extractor, what it does is generates a perfect sample in the sense of the first slide, in the sense of the, sampling the population. While we don't know which will be good here, many, like 99% of the sequences here will be as good as random. And so many of them will produce the right result, and so when you take a majority vote, you'll get the correct value with very high probability. I want to stress, first of all, that this long line of work, over 20 years of work, but I want to stress here that really the first extractor, of course, it was not phrased like this in the Endre Szemerédi paper, but it did contain the very first extractor. It was done for different reasons. It was created from expander graphs, which were mentioned before. It was to do another de-randomization task of small space probabilistic algorithms, but it did contain the seed for the first extractor. And another point I want to make is that extractors and many other pseudo-random objects often yield sort of unlikely and unexpected benefits. In this case, many other applications, some of them have no notion or no need for randomness. So in error correction, you are trying to fix something, and extractors seem to just give you what you want. So anyway, it's the usefulness of pseudorandomness. Let me conclude with the most, maybe the most extreme or worst situation possibility of all. What do we do if there is no randomness at all? So we saw applications of randomness. Now there is no randomness. I mean, which of the applications survive? Well, it's not clear that any should survive, but I want to show you that, in fact, all applications in which you have an efficient probabilistic algorithm, efficient, I mean polynomial time, can survive. Well, let me explain under which assumption. So we want to simulate probabilistic algorithms without randomness at all. We don't have these coin tosses. They don't exist. So we don't even have the sunspots. So what do we do? Or what can we use? And the key is that we can use computational hardness in order to replace randomness. So this is what's called sometimes the hardness versus randomness paradigm. We'll use the assumption that P is different than NP. We'll just use the assumption that some problems are exponentially hard, like maybe the traveling salesman problem. Of course, it may be false, so it's an assumption, but this assumption can replace randomness. Hardness can replace randomness. Because this assumption alone, or something quite like it, not precisely, will generate, just like the randomness before, we can generate deterministically a collection of sequences that are as good as random sequences, in the sense that if you try them all on your original algorithm, see what it does, and take a majority vote, you'll get the right answer. And moreover, because it's all deterministic, if you get the right answer, there is no probability anymore, so the output will be correct always. Again, summarizing, if you have some hard enough computational problem, then every efficient probabilistic algorithm can be replaced with an efficient deterministic algorithm. So we don't need the randomness for all of this. That's a perfect sample. Again, it's a long sequence of works, and starting from cryptography, and that's the summary. Every efficient probabilistic algorithm has a deterministic counterpart. So to conclude, I think I want to stress this, that randomness is really in the eye of the beholder. This is a pragmatic and subjective definition of randomness that is important. Pseudorandomness comes to specify which kind of users do we have for our random coin tosses, and it's a very rich area of collaboration between math and CS. Many applications of randomness survive in worlds in which we have very little randomness, or we have no randomness. And that pseudorandom objects like extractors, like expanders, are extremely useful for other problems in which randomness is not part of the definition. Thank you.